Okay. Okay, so what we had been discussing is the dynamic binding. Okay, and we have seen that if you define a function as virtual, okay, what happens is that you basically trigger the mechanism of dynamic binding of that particular member function on. Okay, so okay. So now, uh, let us see. So, of course, we have sort of, discussed the idea of upcasting on a hierarchy, right? So we know that the inheritance hierarchy can be used to upcast pointer types, okay? And then I mean, it is safe to upcast something to a higher level class, okay? And then so we will see one more example shortly, okay? But so that is allowed, okay? So one fallout of that is that so many a times you are doing a constructor which allocates some objects of a data, okay? So for example, let us see here, okay? So this B is a base class and D is a derived class, and B has some data and derived class has some other data. Okay. So obviously in the destructor, okay, you will so if this data was, let's say, something that was allocated by in memory or something like that, okay, so using a new operator, then in the destructor you would delete this, okay, so you would call a delete on this, okay. And like here in D, you have called a delete on this PTR underscore. Okay. Now, what happens? So suppose you create two objects, one of type B, other of type D. Okay. But even the D type object you assign to a pointer which is of type B. Okay. Now, what happens when you call this delete Q? Okay, so everything is fine, but when you call this delete Q, okay, the destructor of B is called. Okay, so when you say new D, the constructor of D was called. Okay, so this pointer to new int 2 was actually executed. Okay, but when you called delete Q, okay, you are only passing the pointer and the type of the pointer is actually B. Okay. And this is a fairly common use case. Okay. That you actually create pointers of the base class type, but you assign objects of derived class type to that. Okay. We have seen cases and we'll see cases like that. Okay. So what is happening here? So your this destructor is not called, okay, and hence this delete PTR is not called, okay. So this is a problem, okay. So how do you solve this problem? Okay, so so you can solve this problem by simply defining the destructor virtual in the base class. Okay, so if you define the destructor as virtual in the base class, then you know that because of the dynamic binding, okay, when you call delete Q, okay, it will actually bind to the destructor of the actual object type and not statically bind to this particular destructor. Okay. So then what happens? So then basically here the destructor of D is called, and then destructor of B is of course called, because there is an object of type B inside the object of type D. So both destructors will be called. Okay. And hence the proper delete operation will happen. Okay. So this is the other thing that it many times it makes sense. If you are creating a polymorphic hierarchy, it makes sense to make the destructor of the base class polymorphic. Okay. And any other class you may wish to derive later. Okay. Okay. Okay, so now so we will see about slicing. Okay, so basically what happens is that if you do like um, um, so if you call something like, let's say some pointer of type B, and then you call any method, what it does, it basically looks at the, so in case of static binding, it basically only looks at the sub object of type B inside this object of type D, okay, and does whatever it does. Okay, so this is very important to understand. Okay, yeah. Okay, so okay, so yeah, so I think this is clear. Um, okay, now now there is another concept related to this whole virtual function concept called the pure virtual function. Okay, so now consider this kind of a polymorphic hierarchy where you have at the top of the hierarchy the class shapes. Okay, so shapes is kind of an abstract concept, you can say, and then inside shape you have polygons. Okay, and inside polygon you have two special type polygons, triangle and quadrilateral, and then again inside shapes you may have this kind of a virtual object which is called closed conic. So any kind of rounded shape. Okay, any kind of rounded shape without edges, let's say, you can call those closed conics. Okay, and so basically so then ellipse is a special case of a closed conic and circle is a special case of a closed conic. Okay, now consider a function draw that you want to implement. Okay, so you can definitely draw a triangle, you can definitely draw a quadrilateral, you can draw a ellipse, you can draw a circle. So all for each of these draw function can be implemented. Okay, probably for polygon also draw function can be implemented. Okay, but can you implement a draw function for shapes? You cannot. Okay, because shapes is just too general to have this draw function. Okay, but all shapes must have a draw function. Okay, so all actual shapes should have a draw function. Okay, it is not like the draw function is property of only a triangle or only a polygon. Actually, all shapes can be drawn. It's just that this particular shapes class is too abstract to have a concrete implementation of the draw function. Okay, so how do you do this? So how do you capture this kind of a thing situation in C++? Okay, so yeah, so yeah, I think I have already described this problem. Okay, so the way you do that is by having a pure virtual function. Okay, so what is a pure virtual function? Pure virtual function is a virtual function which has a signature but no body. Okay, so if a virtual function has a signature but no body, then it is considered to be a pure virtual function. Okay, now if there is a class which is called which has a pure virtual function, such class is called an abstract class or an abstract base class. Okay, so what does this mean? This means that if a particular class is an abstract class, okay, or an abstract base class, okay, this particular class, an object, an instance of an abstract class cannot be created. Okay, so no instance can be created for an abstract base class. Okay, now obviously then it does not make sense to have a constructor or a destructor for an abstract base class. Okay, But an abstract base class may have other virtual and non-virtual member functions. Okay, so that can happen. Okay. Okay, now data members in a abstract base class should be protected. Yeah, so basically, yeah, okay. Then member functions in an abstract base class should be public. Yeah, because they have to be implemented. Yeah, so yeah, I mean, this is like a general guideline. Okay. Yeah. And a concrete class, which is not an abstract class, so must override and implement all pure virtual functions so that it can be instantiated. So that is the basically the usefulness of this pure virtual function mechanism, that it provides you with a way of saying, look, I am providing this pure virtual function, so you cannot instantiate my class, but through this class, I am telling you which all functions should be implemented by you as a user. So let's say you are providing a library which has an abstract base class. Okay, then you are telling the you are telling the implementer of this library that please implement this member function. Okay, which I have defined as pure virtual functions, so that you can actually instantiate an object of the class that you define. Okay, after implementing these things. Okay, so this is the basically the semantics of the things. Okay, so this is just an example that we just showed. So we have shapes. Okay, then we have polygon, closed conics, which takes shapes. Okay, now here there is a implementation. So polygon has a implementation. So let's say you say draw by triangulation. Okay. Now the draw function then triangle again inherits polygon. Okay, but it re-implements that there is a easier way to draw a triangle, which is just draw by lines, or even for quadrilateral. Okay, draw by lines. Okay, so you can draw very easily these two. Okay, so you have provide maybe more efficient re-implementation of draw functions for this particular things, and so on and so forth. Okay. Closed conics, again, you don't implement anything, because again, closed conics is a virtual type. Okay, so you can't really draw, and since you cannot draw, you basically inherit this virtual function. Okay, so this is how you define, by the way, the virtual function. So you say virtual void draw is equal to 0. Okay, so this is a pure virtual function. Okay. Now, yeah. So
equal to is just an syntax, or it specifies something.
sorry, I could not. So equal to 0 is how you tell that this is a pure virtual function.
So just it is just a syntax of defining a pure.
Yeah, this is a syntax of defining the pure virtual function. Okay, so which is to say that this is a pure virtual function. This has to be re-implemented. So this cannot be implemented, so otherwise somebody may say that, here you can say shapes : draw and re-implement it. That is not allowed. So you have to re-implement it only in a derived class. Okay, so this is what it is saying. Okay. Okay. So okay, and then so the rest of it is easy. Okay, so I think this is clear. Okay. Yeah, so this is the main thing, that instances of shapes or closed conics cannot be created. So the compiler is kind of providing you with a mechanism to enforce implementation of these pure virtual functions. So the idea is that without implementing these pure virtual functions, okay, you cannot instantiate an object of this type. So there may be many other things which are already implemented in the abstract class, okay? But you cannot utilize that functionality unless you sort of implement these pure virtual functions, okay? Okay, so so let me just clear this, okay? Okay, yeah, so yeah, so the other thing is that a pure virtual function may have a body, but it does not matter, okay? So this pure virtual function, if it is a pure virtual function, then still all of the things apply, okay? Okay. Okay, so any questions about this part? Okay, okay, so let us now go into the example that so we will go fast over this example, okay, in the interest of time, okay. Okay, so okay, yeah. So this is the problem that I was talking about. We were briefly discussing that. Let's say you have an organization and you are implementing a salary processing application, okay? And you have two types of employees or staff, engineers and manager. And later you may also add another staff, which is like the another type of staff, which is the director, okay? So how do you do the design, okay? So let me just directly go to the C solution. Okay, so what do you have to do? You have to create engineers and managers. Okay, and this can be done using structs. Okay, you have to initialize, so you can have initialization function. Okay, now you need to create this staff object. So what should this staff object be like? So staff object should be implemented using a union. Okay, so union feature, in C can have one of many different types. Okay, so you can use a union to create a staff object, and then you can have an array of staff in order to in order to have a list of all staff. Okay, and then what you can do, so this is one part. Now let's say you have different salary processing functions depending on the kind of staff. So engineers have different salary structure, managers have different salary structure. Okay, so then what do? You basically have to have a way of you have to have a special field which will also tell the type of the current staff. Okay, so let us see, and then you have to use function pointers or switch mechanism to actually call these guys. So let us see this. So you have this enum type, which is the either engineer or manager. Okay, and then you create this you create engineer, and you have a salary processing engineer, and you have manager and salary processing manager, and then you create this staff, which is a union of engineer and manager. Okay, and now you call yeah, and then you can store all of them in a list. Okay, and then you can just say that if staff dot type is let's say is engineer, okay, is ER, then you call the function salary process engineer. If staff dot type is basically MGR, then you call the salary process manager. Okay, so this is how you would implement it in C. Okay, and as you can see, this is a very messy solution. Okay. Okay, and then for director, you have to again add things. You have to change the whole code. Basically, the whole code gets changed. So enum type you have to change. You have to add new types. You have to add new functions. The union itself you have to change to include the director. Okay, all of these will happen. Okay. Okay. Yeah, so I think these things you understand, but yeah, so there are mainly two different disadvantages. Okay, so you are not having any encapsulation, but that is anyway there in C. Okay, the bigger disadvantage is that everything is managed explicitly. Okay, so you have to change, you have to go through the entire code and change everything just to add the director person. Okay. Okay. So let us see how we solve this problem in the C++. Okay. Okay. So recap is done. Okay. So first we try to do a non-polymorphic solution. Okay. So that is we will not use virtual functions. Okay. So how can we do this? Okay. So we will obviously we will say that this manager is an engineer. Okay. We can also say something like there is another staff, and manager is a staff, engineer is a staff also. Okay. But yeah. So then you have a non-polymorphic class hierarchy. Okay. Yeah, so you can have an so how do you have a collection of mixed objects? You have an array of base class pointer. This you can do, we have seen this already. So basically you have an array of engineer pointers. Okay. Now how do you model variations in salary processing algorithm? You have member functions. Okay. Now question is how to invoke the correct algorithm. Again, either you have to use switch or you have to use function pointers. Okay, so this is the thing. So how will you do it here? So you have engineer, and then you have a manager, which is derived from engineer, and the process salary gets re-implemented for the manager, and of course the type. So you still have to maintain the type explicitly, and the type gets set. Okay. Now here you use the same switching kind of logic, that if type is equal to ER, then you do process salary of the staff. Otherwise, you have to explicitly call the process salary of a manager, even though the staff I is of type engineer star. Okay, and how you do that? So you do an explicit cast here. Okay. And then you do a process salary of the manager. Okay. So again, this is, so again, as you can see, adding director is going to be a few changes, less changes, but still a few changes. You have to add to the enum type here. Okay. And then you have to add to the, the switch statement here. Okay. 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 Okay, so yeah, this we have discussed the non-polymorphic hierarchy for adding the director. Okay. Okay. Yeah. So this is the summary of that. Okay. Now, how does so what happens when you do the same thing in a polymorphic hierarchy? Okay. So basically, in polymorphic hierarchy, what will you do? So you will say that this engineer has a virtual process salary. Okay. Okay. And of course, manager has a process salary, and director also has a process salary. Okay. Now, what will happen if you okay, so the manager here also should have a virtual process salary. Okay. No, so actually you don't need. So okay, so let us see. Okay, so so now how are you creating mixed lists? You are creating engineer engineer pointers to engineer type objects, and you are putting managers or directors or anything there. Okay. Now, since the type of the engineer process salary is virtual, so when you simply do this staff I dot virtual salary here, okay, this is a this call will be bound dynamically at compile time, right? So because this function was declared as virtual here, okay? So automatically the right kind of function will be called depending on the type of the object, okay? So this is the basic idea, okay? Okay, so what is the disadvantage? Yeah, so for this particular design, okay, the disadvantage is that it's difficult to add an employee that is not part of this hierarchy. Okay, yeah. So for example, sales division. Okay, so there can be another kind of hierarchy. Okay, which is this particular hierarchy where you have director, manager, engineer, okay, and they are of type employee, but sales executive is not part of this hierarchy, but that the sales executive is also of type employee, okay. But what can happen is that this employee is actually a virtual object. Now you can't have a process salary function for this employee type object, okay. So what do? You use a pure virtual function for the employee, okay. So then you say process salary is equal to 0, okay, and it gets re-implemented in all the derived class and everything works fine, okay. So this is kind of single example, illustration of how these different features. So in what case you need these different kinds of features, okay. So I hope this is clear. Is there any question here? Okay. Okay. So okay. Yeah. So we will talk about the vector thing maybe later when we discuss. Okay. So let us now go to another thing which actually I wanted to cover today, which is a little bit about how this dynamic polymorphism is actually implemented. Okay. Okay, so we have seen this particular example, so no need to recap. Okay, so yeah, so okay, yeah, so this is a good comparison. So what you can see, so we asked this question: how to represent engineers, managers, and director? Answer is use a polymorphic hierarchy. How to initialize objects, constructor, destructor. Okay, how to have a collection of mixed objects, array of base class pointers. Okay, how to model variations in salary processing algorithm. Okay, different class member functions. Okay, how to invoke the correct algorithm, use virtual functions. Okay, so we have seen this particular thing. So this is kind of the summary of what we have done. Okay, now the question is, what do we do, or how do we how does it actually get implemented, this whole dynamic binding thing? Okay, so so what happens is that for any polymorphic type, as we told in the last class also, the compiler needs to maintain some kind of a type information. Okay, but instead, so how does it do that? It maintains this type information indirectly through what is called this virtual function pointer table. Okay, so what is this virtual function pointer table? So for every class, okay, which has at least one virtual function, okay, what it will do, along with everything else about the class, it will also create this. So it will have a class layout. So it will have member, the member data member, it will have the member function code, okay, and all of that will be there, right? Along with that, it will have this virtual pointer table, okay, and virtual pointer table basically is a table. You can say it's like a data member of this particular class, okay, which of this object, which will be which will be done, and then at compile time, what will happen is basically the compiled expression, okay, will call so what will this virtual function table have? So it will contain the address of an implemented virtual pointer, okay, virtual function, sorry, okay. Okay, so for example, here this G is a virtual function, so virtual pointer table will have one only one entry, okay, and this entry is this end so this entry is actually this pointed to this B : G function. Clear? Okay. Now at the time of call, so let's say there is a call somewhere that so now this P is a is an instance of object B, okay. So I mean this instance is B, but P is a pointer to that. So at the time of call, something like this, that P arrow G, okay, what this call will be replaced by is P arrow function pointer 0, and then of course there will be this pointer of type I mean this is the this pointer, okay, P is the this pointer, and 45, okay, which is the input argument, okay. So this is how it will be replaced, okay. Now so you see that this is basically calling, in a sense you can say that this is basically calling a function indirectly through a function pointer. Clear? So that is what this particular compiled expression for the call to a virtual function is doing. Okay. Okay. Now, so at the time, when you are basically running the code, okay. So when you instantiate this B object, this particular thing gets copied here, and then you go ahead with everything, okay. So this is the one thing, okay. Now, when you have a derived class, okay, and let's say you have implemented this virtual function, okay, in a derived class, what will happen? So your object layout will look something like this. So the object has two parts, okay. So object, if you remember, it has a base object component and it also has a derived object component, okay. But when you redefine a virtual function here, okay, actually what happens is, instead of adding a new function, what you do is you replace the the pointer of the existing function with the code for this new function. Okay, so you add a new function, but with the function pointer for the new function. So basically, the virtual function, virtual function pointer table, that remains the same. So this is the virtual function for F. Sorry, for G. Okay, okay. But now instead of the pointer to B : G, here you have the pointer to D : G. Okay, so this is how the virtual function, virtual function call is implemented. Okay, so when you call, so here P is now a object of type D, let's say. Okay. Okay. So then the call to the call to yeah, so the call to this will again, it will make the same call. Okay, but now it will go to ampersand D. Okay, so if P is basically set as D. Okay. 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 Yeah. Okay. Okay. So yeah. So this is the basically the summary. So whenever a class defines a virtual function, okay, a hidden member variable is added to the class, which points to an array of pointers to virtual functions called virtual function pointer table. Okay, or virtual function table, whatever. Okay. Now, these virtual function pointers are used at runtime to invoke the appropriate function implementation, because of course, at compile time, it may not be known. Okay. Okay. So, when when you create an object of basically, let's say a derived class, something like this, the appropriate virtual function pointer address is added to this virtual function pointer table for that object. Okay. So I hope this is clear. Okay. So here is a bit more complicated example. Okay, where what we are saying here is that basically we have a class which has two virtual functions. Okay. One of them gets re-implemented here. Okay. But this G is not re-implemented. And then this B, but G is present. Okay. Without any re-implementation. But here, then again, you derive something from, B. Okay. And here, this particular G is getting re-implemented. Okay. So how will basically the virtual function pointer table look? So this will basically so initially both, so here there are two virtual functions, okay, F and G. So and so there will be two entries in the VFT and the corresponding functions will be there. Now here there are actually three virtual functions. So one virtual function has been added. So you get the first two and then this newly added virtual function. Okay. And now since this one has been re-implemented, so you have replaced this with B : F. This is still a, so G is still A : G. Okay. And B is H is okay, B : H. Okay. Now, when you have the virtual function pointer table for type C, you see here F has not been re-implemented. So you basically get B : F. So the last, the re-implementation of the virtual function. Okay. So this is what is copied here. Okay. Okay. And then, yeah, so here you get C : G, and of course you get C : H. Okay, because both H and G has been re-implemented here. Okay. So I hope this is clear how it works. So any questions? Okay. So okay, so actually okay, if there are no questions, so one thing I just want to tell that there is one, so next week there is a test that you guys have. Okay, so the syllabus for that, so the syllabus for the test will be till casting on a hierarchy, so which we will cover in tomorrow's class. Okay, so let's see, we can start that today. We have some time. Okay, but this is the announcement. Okay. Okay, so let
So
us start. Yes.
syllabus is cumulative or like everything covered from end of first test till today?
Yeah, so end of first test, but you cannot say that it is not cumulative because it's all one single monolithic thing. So you may you will need to use some features of previous things also, right?
Okay, sir.
So okay, so now we get into what is called so some of the details of casting. Okay, so we have already seen some things about the casting. Okay, we have seen what is a so let us see. I think yeah, there's a recap. Okay. Yeah, so here, I mean, so one thing I must point out here is that so there are different types of cast we will see. So currently we have seen implicit and explicit conversions. Okay, and what we have seen, so what is important is that every conversion, okay, whether implicit or explicit, okay, involves some algorithm. Okay, so it's not it's not automatic. Okay, even though a programmer thinks that it is automatic, that is for that is for a initial programmers, like somebody who is just learning to program. Okay, it is it's a feature that is provided that you should be naturally be able to convert a double to a int or something like that. Okay, without thinking too much about it. Okay, but in the background actually some kind of conversion is going on, some algorithm is going on. So it's not like yeah, so some piece of code has to be executed which the compiler actually fills in. Okay. So for example, even for this particular simple thing, like if you say double I by j, okay, it actually fills in this particular code where it casts both of these to double and then returns the temp I by temp j. Okay. 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 So now, of course, we have seen this. So yeah. So we need not recap, right? So built-in types you can cast either implicitly or explicitly. We have seen this. Okay. And unrelated, unrelated types you cannot cast. Okay. Everything leads to error. Okay. Only thing is explicit with pointers is allowed. Okay. And we have seen that in hierarchies you can do yeah, so sorry, this is unrelated types again. Yeah, so we have seen that in hierarchies. Okay, so if B is derived from A, then you can do an upcast, but you cannot do a downcast implicitly. Of course, explicit casts of point. Yeah, so explicit casts are allowed. Okay, of pointers are allowed by you. Yeah. So okay. Okay. And we have seen that upcasting is safe. Okay. Now. Okay. So what are the so what is the problem? So what I must tell you is that C++ actually defines 4 new cast operators. Okay, so these are called const cast, static cast, reinterpret cast, and dynamic cast. Okay, now the question comes that why, why do we have to actually, and it is advised that if you are using C++, instead of using C style casting, you should actually use these cast operators. Okay. So what is the problem with C style casting? So the main problem is that what C style, so one of the thing is that basically in C style, so because there are, these implicit casting in, in C, or there are, so what happens is your data type many a times loses from a, from a reading point of view, it loses the type information. And you have seen many a times that just by looking at division, like, one integer by another integer, you cannot tell what kind of division operation is used, because if you don't, you have to be very, very aware of the type. Okay. So this is one thing. Okay. And of course, the other thing is that since you are not explicitly casting in many cases, okay, the semantics are not clear just by looking at the program. Okay, so this is the problem with this thing. Okay. Okay. So in C++, it performs fresh inference of types without change of value. Okay, so this is the okay. Okay, so yeah, so the second part is important. So when there has to be a change of value, okay, then you can either use implicit computation or you can use explicit user-defined computations. Okay, but the main philosophy in C++ about casting is that in all, whenever it preserves the type information in all contexts. Okay, so by looking at the operation, you can basically figure out the type information. Okay, and we will see. So, and now when you do casting, it provides a clear semantics through cast operators. Okay, so each cast operator has a very clear meaning, and you know exactly what you are doing when you are using a particular cast operator. Okay. 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 So the first, so let us go into the first thing, which is the const cast. Okay. So const cast basically converts types between different constant volatile qualification. Okay. So basically you can either you can use const cast to remove constness or volatility of a particular variable. Okay. Now this usually does not perform any computation or change any value. Okay. So const cast usually does not. Yeah. So basically, yeah. So you can see here what you can do. So in in C, what you could do. So let's say you have this char star C here. Okay, which is this is a const char star C that you have defined. Okay. Okay. Now but you have defined print function which is taking a char star. Okay. If you say print C, it will give an error. Okay, but it will go through. Is there a question?
Sir, sorry to disturb you, but we have some of us have class after this.
Okay, yeah. So we will continue. Sorry, yeah. We will continue with in the next class. So tomorrow we will talk about casting. Okay. Okay then. Okay. Thank you very much.
Thank you, sir.
Thank you,
sir.